Today's lesson deals with looking at the 3D shape of molecules. So up to this point, we've drawn electron dot diagrams to show the bonding, but these molecules actually have a three-dimensional shape to them. And so today we're going to go through how to be able to identify the shape of these molecules by using their electron dot diagrams. So we also draw these positions or these shapes in 3D. And there are symbols that we use to draw this. So for example, a straight line, a regular straight line, just basically means that the bond is along the plane of the paper. So if you were to put the molecule and line it up with the paper, you would basically just form a line like that. The dashed line basically means that that atom is being pushed back towards the back of the paper, and this little triangle or wedge means that that bond is popping out of the paper towards you. Now, this that we're looking for is called VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. And what it means is that electrons will try to stay as far away from each other. And that's because they have a similar charge, so they will move as far away from each other as possible. The other term that we use for this is stereochemistry. So the idea that this is 3D, this is coming from all around, it's not flat on a sheet of paper. So we're going to start going through the shapes, and one of the things that you'll see is that lone pairs and bonds, or bonding groups as we'll start calling them, around the central atom is really important for this, and basically in terms of determining what shape it is and how we draw this. So our first example is going to be a methane, and the formula for methane is CH4. Now, what I'm going to do is draw the electron dot diagram for CH4. So here's carbon with its 4 valence electrons, hydrogen with its 1 valence electron. And so carbon is going to be my central atom. And then I'm going to add the hydrogens around it. So you can see that every atom now has a full valence. Now here is what's important. I need to look at the central atom, and remember that it's just the central atom I'm interested in with these. So in this case, it's the carbon. So I'm not going to count anything around the hydrogens. It's just the carbon that I'm interested in. And what I need to do is I need to count the number of lone pairs. So if you take a look at the number of lone pairs around carbon, it's 0. Okay, there are no lone pairs. If you take then a look at the bonding groups, you'll see that there is 4. Okay, so basically 1 around each hydrogen. And there's going to be a bond angle here. This is optional for you to know. You don't have to memorize these in any way. This is just to illustrate a point a little bit later on. So basically what's going to happen is that these are going to stay as far away from each other as possible. And in a round thing, basically these atoms, if you were to measure this angle, okay, it would be 109.5 degrees. All right? And this is what keeps these electron pairs that are bonding, to the carbon here, that's going to keep them as far away as possible. So how do I draw that? So how do I draw that idea? So what you do here is we're going to use those kind of series of straight lines, dashed lines, and wedges to do that. So here's my carbon. And what happens with these is I'm going to, and this is, by the way, these can orient themselves in any way. So we kind of have decided a fixed way that we draw these when we draw them on paper to illustrate that this is happening. So we assume that this is this one here is along the plane of the paper. So I'm going to draw the hydrogen here. This one we also show along the plane of the paper. And I'm choosing these because this is how it's again done. So kind of like the basis that these diagrams has been developed. This one we show as coming out towards you. So we draw the little wedge coming out towards you. And this one we show as going away from you. Okay, so going towards the back of the paper. And so I'm going to use a dashed line to illustrate that. And that's how you would draw this, this shape, which I'm going to name in a moment here. All right, this three-dimensional shape, we illustrate it by these dashes and these wedges to show that these atoms are moving into and out of the paper. Now, this shape is called tetrahedral. And you know that you have a tetrahedral shape when your central atom has 0 lone pairs and 4 bonding groups. Now, one other thing before we move on to our next shape, do you see in my diagram that I've done here that there is no 90-degree angles that I've drawn in? So I'm not drawing my hydrogens like this, okay? I'm not doing that. And the reason for it is because my bond angle is not 90 degrees. It's actually 109. So again, these 3D kind of illustrations that we do, try to represent as much as possible what is actually happening. So please do not draw any 90-degree angles on there when you draw these, because there really isn't when you're drawing the 3D shape of this molecule. All right, so that's our first one. Our second one is ammonia. The formula for ammonia is NH3. So again, I'm going to do my electron dot diagrams of my atoms. And then I'm going to do the electron dot diagram of my molecule. And it looks like this. All right. So again, I want to focus on the central atom. I want to focus on nitrogen. Again, the hydrogens here are not the central atom, so they don't influence the shape. And so for this one, I can see that there is one lone pair. Okay. So you guys can see here that there's one lone pair. Oops, one lone pair. Now, if you take a look at it, you can see that there are 3 bonding groups. So 1, 2, and 3. So there's 3 bonding groups. Now, for the bond angle here is going to be 105 degrees. And for this one, what happens is that the lone pair kind of pushes down a little bit on these bonds. So what ends up happening is that these bonds get pushed down. And so that's why the number is lower than it is for the tetrahedral. So a lone pair will always push down a little bit more than an actual bonding group. All right, so how do I draw this? So again, here's my central atom. I'm going to assume that this one is along the plane of the paper. Okay. I'm going to assume that this one's coming out. And I'm going to assume that this one is going back into the paper. Okay, so this H with the triangle is coming out at you. This H is going back into and away from you. So that is how I do the 3-dimensional or stereochemical or Vester shape for ammonia. Now, what do we call this? This is called pyramidal, because it actually looks a little bit like a pyramid if you take a look at this diagram. So again, when you have one lone pair and 3 bonding groups, the shape is going to be pyramidal. All right, our next one. So our next one is water. The formula for water is H2O. So here's my oxygen, and here's my hydrogen. So again, oxygen is going to be my central atom. And then I'm going to add the hydrogen. So again, if I look at my central atom, which is my oxygen, and I count the number of lone pairs, I can see that those lone pairs, that I've got 2 lone pairs. And I can see that I have 2 bonding groups. Now, the bond angle is the same as the one before, 105 degrees. So again, you don't have to memorize those numbers. They just kind of help illustrate why we don't draw things at 90-degree angles. And for this one then, if I were to draw it, here's my oxygen, and here's one hydrogen, and here's another hydrogen. Do you notice here that I've got more distance than 90 degrees? Because it's 100 degrees, it's 105 degrees, it's actually a little bit bigger. So, and the other thing about it is that this becomes, there's no dash or wedge. This becomes flat. So if you actually see it, there's a position with this when you spin the molecule that can actually be flat. So you don't actually draw this shape with any wedges or dashed lines. They're actually drawn flat. And this shape has two possible names for it. I tend to call it V-shaped. And the other one that it's called is bent. Okay, so this one has two different names. So again, whenever you draw an electron diagram of a molecule and it's got two lone pairs and two bonding groups, this is going to be V-shaped. All right, our next one. This is the easiest one of all. This is basically hydrogen fluoride. We'll start with this one, hydrogen fluoride. Fluorine has 7, oops, I drew 8 there. Okay, so fluorine has 7 valence electrons. Hydrogen has 1. And this one looks like this. Now we've got a few problems here. First of all is this, which is my central atom? I don't know, right? One or the other, I don't know which one it is. But it doesn't matter because for this one, the moment you have 2 atoms, the only shape that it can be is linear. So this doesn't matter. And this will vary depending on your atoms anyway. So as long as there's only 2 atoms, the shape will be linear. Now, this is sometimes called diatomic linear. And all it means is that there are 2 atoms making the linear shape. Sometimes there's more than 2 atoms that make the linear shape. You'll see another example when we do this. And when that happens, we just call that triatomic linear. But for me, for my purposes, linear is good enough. So you don't have to mention that it's diatomic or triatomic linear. All right, we're almost to the end of our shapes. So our next one is boron trihydride. And I hope that you guys remember that boron is full with 6 electrons. So there's my drawings of the atoms. And now I'm going to do the drawing of the molecule. So there it is. All right, so lone pairs. So again, I look at that boron, I look at that central atom, and I can see that it's got no lone pairs. And how many bonding groups do I have? And I have 3 bonding groups. And I'll talk about what I mean by pairs and groups here with our next example. Now, the bond angle with this is going to be exactly 120 degrees. And I don't know if you guys know this, but that basically is the angle in an equilateral triangle. So what ends up happening with this is this looks exactly like an equilateral triangle. So when you draw this, you actually want to draw it like this. And we're just going to change the color here and show you guys that it looks like an equilateral triangle because the bond angle is 120. Now, the name for this is trigonal. And the other thing about this, do you see that again, I've drawn it without any wedges or dashed lines? It's because this is flat. These molecules are actually very flat. So this is called trigonal planar. We're going to do a second example here, and this one we're going to include a double bond. So the second example is what's called methanol. The formula is CH2O. So there's my carbon. There's my hydrogen, and my oxygen has 6. So again, my central atom is going to be carbon. I'm going to bond in my 2 hydrogens. And then what's going to happen, and I'm going to do this just to make this a little bit shorter, is I actually have a double bond. So that's my electron dot diagram. So again, I look at my carbon, my central atom. I know that there's lone pairs around the oxygen, but those are not the ones I care about. I care about my central atom. So here I can see that there are 0 lone pairs, but there are also 3 bonding groups. And so a double bond, so 2 sets of electrons are still 1 bonding group. So a double and triple bond you count as 1. So this one has 0 and 3. And so this one, its shape is going to be exactly the same. It's going to have 120 degrees between the bonds, but one of the bonds, of course, is just going to be double. That's it. But it's still going to have this flat shape, and one of the bonds is going to be double. All right. The last thing that I'm going to do is this last one, and this is carbon dioxide, which is CO2. So for this one, carbon has 4 bonding electrons, oxygen has 6. Carbon is going to be my central one. I'm going to actually go right into the electron dot diagram. So when I did this before, I determined that I needed 2 double bonds. Again, I look only at my central atom. I'm not going to look at the oxygens at all. I'm just going to look at my carbon. I can see that that carbon has 0 lone pairs. Again, I don't care about the lone pairs on the oxygen. And it's got 2 bonding groups. Now, because they're completely opposite each other, and remember, they're trying to stay as far away from each other as possible. So this bond angle is just basically a straight line, which is 180 degrees. Okay, so this one to draw, this will form a straight line. Remember that, you can align it so it's coming out at you or going into the page, but there is a consensus of how we draw these. And so basically it's going to be O double bonded to a carbon, double bonded to another oxygen. And so this is going to be, it's going to look exactly like its structural diagram, right? That's going to look no different than its structural diagram. And this shape, again, it's a line, so it is linear. All right, so that's a review of the shapes. This little table that follows, it's also in your work booklet, and it summarizes everything that you have learned about this. So it basically goes through and it shows the electron dot diagram. It tells you the lone pairs and the bonding groups. It gives you a picture of the shape, and then it gives you a picture of what the 3D molecule looks like. Right? So you've got it for each of these as you go along. You have to memorize these. You've got to know these shapes. And because this will come important over the next couple of days. After then, we start looking at properties of substances. The right shape is important to be able to figure out the properties of these molecules. So we will continue reviewing a little bit of this over the next couple of days to help you feel secure. We're also going to be doing a bit of an online activity to help you see these in a little bit more in 3 dimensions as well. And anyway, this is VSEPR theory, where we're looking at how atoms arrange themselves, the bonds arrange themselves in molecules to keep the electrons as far away from each other as possible around the central atom. And we use lone pairs and bonding groups to determine what the shape will be.